You clicked play. A video filled your screen. 60 images per second, each one sharp, lit, and alive with motion. Your eyes absorbed it instantly. Your brain called it smooth. But in the 16 milliseconds between each of those frames, your graphics card fought a war. A war involving billions of transistors, thousands of processing cores, and a pipeline so brutally engineered it makes a factory assembly line look like a child stacking blocks. You saw none of it. So what actually happened? Your GPU did not draw that frame the way a painter draws a portrait. It did not start at the top left corner and work its way down. It attacked the entire image at once, from every angle simultaneously, using a kind of parallel brute force that no single processor can match. And to understand how, you first have to understand why your CPU could never do this alone. Your central processing unit is a genius at sequential logic. It solves problems in a chain, one step feeding the next, with each calculation building on the result before it. This is powerful. It is how your computer runs an operating system, compiles code, and manages memory. But rendering a frame is not a chain problem. It is a grid problem. A 1920 by 1080 image contains over 2 million pixels. Every single one of those pixels needs a color value, a lighting calculation, a depth check, and a texture sample, all at the same time. Your CPU has between 8 and 32 cores. It would take it hundreds of milliseconds just to touch every pixel once. Your game would run at 6 frames per second. Everything would feel like moving through wet concrete. Your GPU has a different answer. A modern GPU does not have 32 cores. It has thousands. The RTX 4090 has over 16,000 CUDA cores. Each one is small, simple, and nowhere near as intelligent as a CPU core. Think of them not as professors, but as first graders who are very, very fast at multiplication. You cannot ask a first grader to write a novel. But if you need 2 million identical math problems solved right now, you hand each one to a different first grader, and every answer comes back at once. This is the fundamental architectural insight that changed real-time graphics forever: massive parallelism. But the frame has not started yet. Before a single pixel is colored, your GPU has to know what it's supposed to draw. That information comes from your game engine, which packages up a list called a draw call. A draw call is a set of instructions that tells the GPU what geometry to process and what rules to apply to it. Think of it as the blueprint handed to a construction crew. Without it, all those thousands of cores are just sitting idle. The blueprint arrives. The pipeline begins. The first stage is called the Vertex shader. Your 3D game world is made of triangles, thousands of them, tens of thousands. Every object in the scene, a wall, a weapon, a face, is a mesh of connected triangles, and every corner of every triangle is called a vertex. In the vertex stage, your GPU takes each of those points in 3D space and projects them onto a flat 2D plane. It is performing the same calculation a camera does when it collapses a three-dimensional world onto a flat film frame. This stage runs in parallel across every vertex in the entire scene at once. The triangles are now flat on screen, but the GPU does not yet know which pixels those triangles cover. That's the job of the rasterizer. Rasterization is the process of converting a triangle, a mathematical shape with no inherent pixel size, into a grid of actual screen pixels. The rasterizer looks at each triangle and asks, for every pixel on screen, is this pixel inside this triangle? If yes, that pixel is assigned to that triangle and passed forward. This happens for every triangle across every pixel. The speed of this process is measured in gigatexels per second, billions of texture samples handled every second, because anything slower and you fall behind the clock. Now comes the stage most people associate with modern graphics, the fragment shader, sometimes called the pixel shader. This is where each pixel gets its final color. The fragment shader is a small program that runs once per pixel and calculates lighting, shadows, reflections, and material properties. It asks, is this surface metal or skin? Is the light source above or behind? Is this pixel in shadow or fully lit? These are not simple questions. A fragment shader for a AAA game title can be hundreds of lines of code, and it runs 2 million times, once per pixel, every single frame. This is where Amdahl's law becomes brutally relevant. Any part of the pipeline that cannot be parallelized becomes a ceiling on your entire frame rate. The fragment shader was historically the bottleneck. More shading, more bottleneck. Hardware engineers spent decades designing wider and wider shader arrays to push through this ceiling. It's why GPU generation over generation performance leaps are so dramatic compared to CPUs. You're not making one core smarter, you're making 10,000 cores available. But shading alone doesn't make a scene convincing. Light in the real world bounces. Shadows have soft edges. Reflections curve around surfaces. For decades, games faked all of this with tricks and pre-computed data because calculating real light bounce in real time was computationally impossible. Then came ray tracing. Ray tracing reverses the direction of light. Instead of calculating where light goes from a source, you fire a ray backward from each pixel on screen out into the scene and ask, what surface does this ray hit first? Then you fire more rays from that surface, calculating what light reaches it, what reflects off it, and what shadows fall across it. The cost is enormous. A single pixel might require dozens of ray casts, 2 million pixels times dozens of rays each. This is why dedicated ray tracing cores exist on modern GPUs. Hardware silicon built for nothing but ray intersection math offloaded from the shader cores entirely, so neither job slows the other one down. The frame is nearly complete. Every pixel has its color, but it hasn't left the GPU yet. The finished image is written into a region of memory called the frame buffer. Your GPU typically holds 2 or more of these, one the GPU is currently drawing into, and one the display is currently reading from. This is called double buffering or triple buffering at higher frame rates. The reason is simple. If your display read the frame buffer while the GPU was still writing into it, you'd see a half-finished frame on screen. The top half would be from one frame, the bottom half from the previous one. A visible horizontal tear. With buffering, the display reads one complete image while the GPU prepares the next, and they swap only when they're both ready. 16 milliseconds have elapsed. The buffers swap. The new frame hits your screen. You didn't see triangles or vertices or fragment shaders or raycasts. You saw a puddle reflect a streetlight. You saw a shadow stretch across a wall. You saw motion and light and the illusion of a world that doesn't exist. Your GPU rendered it all. 16 milliseconds, 2 million pixels, thousands of cores running in perfect, violent, parallel silence. You clicked play, and without a second thought, you believed every frame.